Okay, we're starting chapter 6, solving and graphing linear inequalities. So we begin with something that you should be feeling comfortable with, solving inequalities using addition and subtraction. So we are going to do a little graphing of a linear inequality in just one variable. When we graph in one variable, that means there's only one variable in the statement that you're given. What does that look like? How many dimensions do you need to graph in one variable? Anybody? Okay, so when graphing in one variable, you only need one dimension, which looks like what? What's a one-dimensional graph? It is a what? Does anyone see a one-dimensional graph in this room? It is, yes, say it. A number line. It's a number line. So when graphing in one dimension, we're going forward and backward, right? It's the set of points on a number line that represents the solutions. So you don't need to take down this little statement, but let's see if we can write, or if we can graph the inequality that describes this. The lowest temperature recorded in Antarctica was negative 129 degrees Fahrenheit. And it was at the Russian Vostok station in 1983. So using only this fact, that the lowest temperature recorded was negative 129, graph an inequality that describes the temperatures in Antarctica. Okay, so here's Anthony's answer. We have a number line because the temperatures just go up or down, right? Or they stay the same. They only can move in a linear direction. So we graph this on a number line, and then he made a number line that zooms in, and you can see negative 129 degrees right there. And is that number line in standard form? Are the numbers on the right greater than the numbers on the left?
Yeah, but
They are. So this is good. This is a good number line because as you go to the right, negative 128 is greater than negative 129. So this is good. And the question says, or the facts up there state that the lowest temperature recorded was negative 129. So he starts there, and then he's showing you greater than that, right? Does that make sense?
Yeah.
One thing he did, though, at negative 129, look at the type of graph he has there. What is that? That's a circle. Do you see that? And it looks like there's space in there. So that would tell you, if you leave an open dot, that would tell you that that actual value was not included in the set. Is negative 129 degrees a possible temperature? Was it a temperature in Antarctica? So instead of leaving it open, we would make that a solid dot. Otherwise, this is beautiful. Okay, and he was able to use two colors up here. On your paper, you just bold it. You can use the same pencil, just bold it. Okay, now number 2 and 3, we are given a graph. Notice that we see that open dot here and a closed dot here. See that? So that's going to affect the statement that's made, right? And they're also pointed different directions. And of course, they're at different locations too. So who could come up and write the inequality that represents number 2? Do it at home and check your work. Okay, so Dylan says that for number 2, he starts with y, and then he says y is actually all the values that are less than or equal to 8. That's what he said, and he wrote this kind of from right to left, right? So could we write this from left to right? If we wrote y, we could turn that inequality sign around, right, and say this. Is this a true statement that he's written? Why did you choose less than or equal to?
Because it's also equal to 8, and if I did not...
How do you know it's also equal to 8?
Because it's on that point.
It's on the point, but is it a solid dot?
No.
It's an open dot, right? So is it actually equal to 8?
No.
No. So instead of less than or equal to, we're going to just say less than. This is what the graph looks like. So the y values are less than 8. 8 is like the boundary line, but the y values never do equal 8. Okay? Okay, so once again, he started with the number, and the y value is on the right. So if we read it in terms of the y, we would say y's are greater than or equal to negative 2.5. Does that make sense? So usually we like to turn this around and put that unknown, the set here, which means we've got to turn the inequality sign around, right? Y's are greater than or equal to negative 2.5. Okay? And so when you're writing your inequalities, lead with the variable. So when you start, put your variable down, y, and how does it compare to the negative 2.5, right? You can put those both down and then say, oh, all the y's are greater than or equal to due to this solid dot, right? It could be equal to negative 2.5. Good. And also be careful with your number lines because these number lines are beautiful. They're going from left to right, least to greatest, right? But sometimes when people use negatives, they accidentally go negative, negative 5, negative 6, negative 7, negative 8 like this. And that is not standard form, is it? That's not how a number line works with negatives, so be careful. Okay, let's solve inequalities using addition. This is just transformation that you're used to doing, right? I mean, we're used to using inverse operations to do what? To isolate variables, really, right? And when we isolate unknowns, we are finding equivalent statements, right? Today we're finding equivalent inequalities. In the last chapter we found equivalent equations, right? So, feels the same. It's just that we have an inequality sign. So when we transform inequalities, our new statement has the same solutions as the old statement. Just be careful to not lose the inequality sign. We're so used to working with equations that sometimes people drop the inequality sign and write an equal sign. So watch out, especially as we're just beginning this section. Okay, so we are going to solve for x, and then we're going to graph the solution set. So the first inequality is x minus 9 is less than or equal to 3. So when you see subtraction in the expression, what operation will we use? Addition. So what will we add to both sides of this inequality, everyone? 9. So write that down. Show that. You're adding 9 to both sides of the inequality sign. That's now your fence, right? It doesn't change the inequality sign, does it? So the first thing you need to do is come down and put that inequality sign in your simplified expression, right? We have x is less than or equal to what? 12. Good. And then we can go graph this. And so this inequality symbol is less than or equal to. So what type of dot will we have, Grant? Good. He says filled in dot. There you go. And then which direction will it go? To the left. Good. And notice if you put your variable on the left side of your inequality statement, do you see that the symbol actually points the same direction as the ray? Okay? So that's nice. Okay, let's try this one. Is less than negative 5. What will we do to both sides? Add, good. Add 9.2. Add 9.2. And does that change our inequality sign? So we just bring it straight down. Put it in there before you forget. This is not an equation. On the left side, we have p is less than, and then be careful. What do you need to remember when adding decimals? Line them up, right? So the 5 could be written as 5.0. And we now have a negative and a positive. So it's going to be positive. That's right, because the greater absolute value is positive. So what is our answer? 4.2. Good, 4.2. And so we need to see 4.2 on the graph. So we could have, literally, we could put 4.2, and I could do 4.3, 4.4. We can make a graph like that if we want. Really zoomed in on the tenths, right? And will the end of the ray be open or closed up? Open dot. Good, that's a less than sign, so there's no equal. So put an open dot. And then which direction if you're less than? To the left, as long as you have a standard number line that's going least to greatest, right? Okay, try that, come back and check. Okay, so a little trickier, moving things to the left. And then notice we rewrote the inequality with the variable in the first position, right? And then look at that, the inequality sign points the same direction as the graph. This is the graph, right? This is the inequality statement. Okay, so let's jot down what we need to remember when using the addition property of inequality. If we're using the addition property of inequality, what operation are we operating on, or what do we see in the statement?
A negative.
We see, good, subtraction. When we see subtraction, we use addition, right? And so we will add the same value to both sides of the inequality. So as a rule, can you finish this? If A is less than B, then we simply can say A plus C is still less than what? Say it, Wesley? Good, B plus C. So if this statement is true, then when we add the same value to both sides, the left is still less than the right. Okay? The subtraction property of inequality must mean that we're doing what to both sides? We are subtracting, right? Subtracting. It's the same with equations, right? And so we would say if A is less than B, then who can finish this? Lexi. Still less than. Good job. So this is how we can show it in the form of a rule. Okay, so you are ready to begin. You know, you have a lot of time in class. I really hope that you will put a lot of energy into every challenging word problem that you can. It's going to pay off for you, big time. So